with normal distributions, again, the normal distribution is when we're using z-scores. So that's our normal curve. If a random variable x is normally distributed, you can find the probability that x will fall in a given interval by calculating the area under a normal curve for the interval. That's what we were just doing. So we look at this, we want to find the area, that blue area there. We can find that, that's what we were just doing, but we were using z-scores. This I probably would write down. Probability of a standard normal distribution. The way we're going to find the probability of a standard normal distribution is either use the chart that I gave you last time, which apparently Michael wants to do because he didn't want to get up to get a calculator. You don't want to use that chart, do you? You want to use the calculator, right? Practice. Please, Mike, get up and get a calculator. So use one of those. All the x's have been changed to z-scores. That's for the standard normal distribution. You're changing everything into a z-score. If we're just doing if we just have a normal distribution, then what we can do is convert to z-scores, then use this. And I'm going to write an or up here. Or you can use the calculator. That would be number 3. Now I'm going to show you how to use the calculator. Even I learned sometimes, Carson, I figured out, hey, there's an easier way than what the book teaches you on this one. This formula is important though because we're going to change scores into z-scores. You're going to have to know how to change a raw score to a z-score. Even though a lot of the times we'll let the calculator do it for you, guarantee it on the next test, I say, what is this score as a z-score? What is this score as a z-score? So you've got to be able to change a raw score, maybe your 1924 here that you scored on the SAT, you got to be able to change it to that z-score. And again, all a z-score is, it allows us to compare numbers that normally we wouldn't be able to compare to each other. Maybe you compare your history exam score to your phys ed exam score. Normally you couldn't compare those two, but if we change them both into z-scores, then we can compare. You can say, hey, on the history exam I was 1 standard deviation above the mean. On the phys ed I was only a half a standard deviation above the mean. So you did better on the history exam. Something that we'd normally use that for, or what colleges would use, SAT and ACT. Some schools push to take the ACT, some schools push to take the SAT. Well, when a college gets all these different students coming from everywhere, and some people have taken one, some people have taken the other, they can compare it by changing everything into a z-score. Saying, okay, this person on the ACT, this person was 2 standard deviations above the mean. Well, this person was 1 standard deviation above on the SAT or ACT, whichever one I didn't say. And they can say, we want this person because they were higher. Even though it's not the same score, it's not the same test. So probability of the normal distribution. We're looking at this area, we talked about this already. That area, if you change it to the standard normal distribution with the z-scores, that area is going to be the same as the probability. We change it to this, whatever that area is, and the probability are exactly the same. So if this came out to be about 76% of the area, then the probability is 76% that you're going to fall in that range. A survey indicates that people use their cell phones an average of 1.5 years before buying a new one. Standard deviation is 0.25. So this is our sigma. This is our mu. A cell phone user is selected at random. Find the probability that user will use their current phone less than 1 year. So we want to find the probability that your X is less than 1 year. If you're, who's the people that make the phones now? What phones do you have? What? Apple. So if you're Apple or Samsung, might this be important to know how long somebody's going to keep their cell phone? What do you think they want? They want you to keep it for a bunch? Nah, they don't like people like me who keep phones for 7-8 years, all right? And I still would have my old flip phone if it wasn't for the fact that I had to switch up because my family wanted to switch up. So they don't like people like me because they want you to go out and buy a new phone. As a matter of fact, the iPhone or whatever, well, they put out 2 new ones every year or something so that you have to go out and buy the new updated version of it. I think they probably do. They make little things in there so that, hey, we're going to make this change, and then the old one won't work as well, and they'll want to go out and buy a new phone. So we want to know, if this is our company, we want to know what's the probability that a person only keeps the phone less than a year or less. Okay? So we're looking at this. This is what our normal curve would look like. 1.5 is our mean. We want to know this area down here, a year or less. 0.25 is the standard deviation, so we'd be somewhere like here, 1.25, and then the next one would be there. So this would be 2 standard deviations away. Well, if we're looking at it this way, with the raw scores in here, these are raw scores. We're looking at just the normal numbers, the raw scores, not the z-scores. We can't actually figure out the area every time because every time it's going to be a little different. So we need to change them to z-scores. The way we change it to a z-score, x minus mu divided by sigma. Again, your value minus your mean divided by your standard deviation. And we figure out that 1 year, keeping the phone 1 year matches up to -2 standard deviations away from the mean. So what do we know about this? Is it going to be usual for somebody to keep a phone a year or less? No, not unless you're Sean and you break it every couple of months, and you don't do that. So it's going to be unusual. This should be very unusual for this to happen. And you could probably guess about how much is that area right there. If it's an unusual event, what do you know? It's less than what? Alright, well, if it's unusual, it's less than 5, right? But we know if it's 2 standard deviations, it's probably going to be that 3.5 or something, 3.25, something like that. So it's going to be something less than 5% of the time is somebody going to use a phone for less than a year. But you got to be able to do this. You got to be able to change it to a standard deviation, or I'm sorry, to a z-score. And it comes up to be about .0228%. Or 0.0228, which would be about 2.3%. Again, very unusual for somebody to keep a phone less than a year or less. The average speed of vehicles traveling on a stretch of highway is 67 miles per hour with a standard deviation of 3.5 miles per hour. A couple years ago, this probably is when this study was done, just a couple years ago, because about 4 or 5 years ago, what happened to the speed limit on the highway?
Did it go up? It was like 65.
It was 65, and now most of them are 70.
I didn't know there was a place that's actually removed.
Yeah.
Because on 35
Yeah, so, some of them. Now, it's got to be an actual highway like 75 or 70 or something like that, and you can't be going through a city area, all right, or a urban area or whatever they consider it. So if you're out on 70 and you're going through Richmond, the speed limit might go down, all right, in some spots. But if you're, and I don't remember because I haven't been on 70 over that way for a long time, but if you're going from here to Dayton on 70, it's 70 miles an hour now. It used to be 65. And they probably figured this out, hey, the average speed's 67 anyway. We're not having any more crashes than we did in the past. Why not raise the speed limit to 70 miles per hour? All right, so what we're going to do on this, to figure this out again, sketch your graph, find the z-score for 70, find the area to the right of the z-score, and then we'll interpret the results. Probably should have made sure I read the problem. So this is our mu. Somebody help me out and remember. Mu is 67. Our sigma is 3.5. Mu is 67. Sigma is 3.5. So what's going to go right here? What's our number going to be right there? 67. All right, since our sigma is 3.5, all we're going to do is take this number, add 3.5 to it, so we'd be at like 70.5 there. Add another 3.5 to it, that'd be at 74. Add another 3.5 to it, that'd be 77.5. 1, 2, 3 standard deviations above, then 3 standard deviations below. What's that, 63.5? Take a 3.5 away from that, that'd be at 60. Take a 3.5 away from that, that'd be 56.5.
All the people that are doing like 56 driving nuts.
All the people that crash all the time drive me nuts. So we have this is our drawing. We want to know, if I go back to this, we want to know what is the probability, if a vehicle is picked at random, what is the probability it is violating the 70 mile per hour speed limit? So we want to know what's the probability that it's going above 70 miles an hour. So we'll say that right there is 70, somewhere about in there. So which side do we want? Left or right?
Right.
Alright, stupid thing. We want this right side. We want this area. That's going to be our probability. Now the bad thing with that is we can't actually find that until we change it to a z-score and then do all this other stuff. Alright? So we're going to change 70 miles per hour into a z-score. The way we change it to a z-score, we take 70 minus 67. 67 was our mean, right? Divided by 3.5. Somebody help me out with the calculator. What's 70 divided by, or 70 minus 67 divided by 3.5? So that's our z-score. So if we were on our normal curve looking at z-scores, that would be 0. We'd have 1 here, 2 here, 3 here, -1, -2, -3. This is for z-scores, same curve, just 2 different sets of numbers, we're gonna be right about in here at 0.857. These two graphs are exactly the same, just one in raw scores, one in z-scores. That makes sense? Michael, that make any sense? This one's in raw scores, the numbers, miles per hour, all that stuff, z-scores. We want to find that area. Again, we can grab our calculator once we have that. You found it already? 0.1957. That's the area. That's also the probability that we're gonna see somebody breaking the speed limit. So if you got a cop sitting out there, about 20% of the cars that go by that cop are gonna be doing what? 70 or more than 70. They're gonna be breaking the speed limit. And that would be our interpretation. What's that tell us? Tells us that 20% of all the cars out on the highway are going faster than the speed limit.
It's kind of low.
Yeah, it probably is. It's probably low because that mean is 67. Now you gotta, you might say it seems kind of low, but then you gotta remember too, you go by somebody and they fall way back behind you as you're on the highway, and you're not even thinking about that person who was doing 55 or 52 or something. So those people who are doing 52, what do they do to this mean?
Pull it back.
They pull it way down. There might only be 2 or 3 of them, but since they're sort of outliers, they pull it down a whole bunch. Survey indicates that for each trip to a supermarket, a shopper spends an average of 45 minutes with a standard deviation of 12 minutes in the store. The length of time spent in the store is normally distributed and is represented by the variable X. A shopper enters the store, find the probability that the shopper will be in the store between 24 and 54 minutes. Any reason that you might want to know that a shopper is staying in your store longer or shorter time? If they're staying in the store longer, what's that probably mean?
Buying stuff.
Maybe they're buying stuff. Or maybe Grant's right, maybe they can't find what they're looking for, so you probably need to change your store up, because if they can't find it, what are they going to do next time?
No, go there.
They're going to go somewhere else. So you might, that might be something you need to figure out. Hey, are they staying in the store because they're wanting to buy more stuff? Are they staying in the store because they can't find anything? Now, when I went to where Michael works the other day, and I seen him came in, we were out the door. Made sure that he didn't fix my food. You didn't even know I was there, did you? I seen you back here. That other guy that was working back here, he didn't know what he was doing, did he? On this, so this is, somebody help me out again. That's our sigma. This is our mu. So that when I switch this slide, it's got it on this slide. So what we want this time, we're looking at this. This is our curve. What's this number right here going to be? 45. What's this one going to be? Remember, if you go up 1, 57. Just add that to it. 69. 81, is that right? What's this one going to be?
That would be
33. 21. Oops. 9. Sorry, my pen isn't putting stuff where it's supposed to be. So that's what our curve would look like. Now, if we want to change this so that it's got z-scores on it instead of those raw scores, we got to change that 45 into a z-score. Or actually, we want to find these. We want to find these z-scores. So we do 24 minus 45 divided by 12, and we would do 54 minus 45 divided by 12. Now what I'm going to show you, so we could find that in our, again, our Z graph, the one with the Z-scores on it, it's just going to look like that. Looks the same every time. So we want to be between 24 minutes, that's somewhere about in here, and 54 minutes, somewhere about in here. We're looking at that area right in there. So on our Z-score down here, we'd be somewhere about there. We're about almost to 2 here. We're looking at that area. Same graph, just raw scores, Z-scores. Now instead of doing all that, changing all the Z-scores, I want you to know how to use the Z-scores. But what you can do on your calculator is it'll allow you to do it without changing everything to Z-scores. So if you grab your calculator, I'm going to show you how to do this. It's basically the same steps as what we were doing. You're going to take second bars, go to the normal CDF, and instead of have to punch in what the two Z-scores are at your lower and higher limit, we can punch in these raw scores. All right? And if you're on the new calculator, that's why it asks you what's mu and what's 1. Right? Because you can, or I'm sorry, what's mu and what's sigma? Because you can put in the actual mean and sigma. So we can just put these in. So what we want to put in, our lower limit, 24. If you're on the old calculator, you put in 24, comma. Your higher limit, or your upper limit's 54. Put that in, comma. Then you put in your mu, which is 45. Comma, then you put in your 12, your sigma, your standard deviation. Close the parenthesis, hit enter, and it comes up to be about 0.7333%. Does that look like that's about 70%? My graph doesn't look like it, does it? Looks like it's more like 60% or something, but my graph must not be drawn very well. So we're saying about 70% of the people spend between 24 and 54. Somebody get something different? Because maybe I messed up.
I got that.
Got that? So we're looking at this. This is our graph between 24 and 54 minutes. Those are our raw scores. We change them to Z-scores, which we didn't bother to finish it out, change it to Z-scores, but that's what they would be as Z-scores. So we'd be at negative 1.75 up to 7.75, and that's about 77. Is that what we said? We said 73, didn't we? I did get 77. If you change them, I know why. If you change them to Z-scores, oh, no, this is why. Because see what they're doing here? They found this whole area, then you got to subtract this off, which is dumb. The calculator will do that for you. Puts us at 0.7333. Right, this is how you do it on the calculator. So this is what you probably want to write down there. Instead of changing everything into a Z-score, the calculator will do all that for you. And we can find the probability or the area by just doing this. You might want to write down, this is using using the raw scores. This is for using the raw scores. The three things that you wrote down earlier, you might want to put on there, go back and put on them. Those are for using Z-scores, when you have the Z-scores. All you're going to do on your calculator, same setup, put in the low limit, comma, upper limit, should be another comma there. The mean, standard deviation, another comma there. Close the parenthesis, hit enter. If you're on the new calculator, again, it's just going to ask you and you're going to put them in, just this one, then this one, and then hit enter, and you'll have to hit enter twice, and it'll tell you your area. But please don't get away from drawing something so that you know, hey, I should be about 60%, or I should be about 20%. Got to be able to draw these normal curves and the standard normal curves. Standard normal curve goes with the Z-score, normal curve just goes with any set of raw data. Easy stuff, Shania. Bored to death with me continuing to talk about it because it's that easy, right? You get no rest over break. Michael, did you get all that? Got that one written down? Alright, going back to this real quick, because there's one other thing that I want to make sure we go over. We found this, did all this stuff, and we figured out that the probability or the area here, 0.733, so about 73% of the people stay in our store between 24 and 54 minutes. So if 200 shoppers came in our store today, how many shoppers would you expect to be in the store between 24 and 54 minutes? To figure out how many of those shoppers are going to stay in there in that range, all you have to do is take that probability that you just found and times it by that number. So somebody help me out with the calculator. What's 0.7333?
146.
So about 146.6.
146.6.
So we'll say about 147. Because we're probably not going to have half a shopper. We expected about, Grant, that wasn't you, was it?
What?
That wasn't you, was it?
What?
Gotta be politically correct. You don't hear me saying you have half a brain, do you?
You're like a quarter.
Huh?
You're like a quarter.
Alright. See, I was trying to be politically correct to be nice. So about 147 of the shoppers we can expect should stay in the store between 24 and 54 minutes. Could we go through and see, you know, is it unusual for somebody to stay in the store 10 minutes? Yeah, what might be happening if somebody's staying in the store for only 10 minutes? Why might we want to look at that? You own Walmart over in Eaton. Why might you want to say, hey, that guy just walked in the store and now he's walking right back
Oh,
out?
People stealing crap.
Stealing stuff.
Yeah.
He's going in there, he knows exactly what he's going for, he shoves it in his shirt, he walks right back out. You might wanna say, he's doing something funny. He walked in, walked right back out, and then a half hour later, he's coming back in and he's walking right back out again. Something's going on. My wife used to work at the Kmart over there, and that was one of the things that they watched all the time. You'd see the people walking in, and then they'd walk back out 5 minutes later. And they're all going, well, what's going on? I said, I tell you what's going on, they're stealing something. Because then they'd walk back in a half hour later, walk back out. So about 146, 147 shoppers gonna stay in the store that long. Oops. That move.
Yeah. It's got a new button. Yeah, I see the button on the top.
Do anything.
Should be good now.
All right, that's your assignment, page 252, 1 through 12, 13 through 27, the odd, and then 31 through 34. A whole bunch of these as I was doing them. If Grant started on them right now, he could probably get the first at least 12 done in the 8 minutes that we have, because all you've got to do, punch them into the calculator. Michael doesn't have a calculator at home. Does he probably want to try to do them right now then, maybe get them done? Might make it easier.